Okay, we take up preparation of ethers, and here the first preparation is by dehydration of alcohols. As you can see here, we have dehydration of alcohols, which is the first preparation given. Now you know that generally alcohols undergo dehydration in acidic conditions. The acids which are used here are primarily either concentrated H2SO4, or you may even use H3PO4 concentrated. So these are the two acids used here, and you have to know that the dehydration can be of two types. Intermolecular and intramolecular. Intermolecular dehydration occurs at lower temperature, and it produces ethers as your main products. Whereas intramolecular dehydration occurs at higher temperature, and it produces alkenes as your major product. So basically, dehydration has to be controlled. In order to obtain ethers, we will have to work at lower temperature. Now, one of the examples that they always quote is about formation of diethyl ether from ethanol. So let us take up that formation of diethyl ether from ethanol. I'm sorry, just a moment. Oh, sorry. Oh, doesn't work. Okay. Let us take up that. We start with ethanol, and there are two different preparative routes. We use, the first route goes like this, and here we have 443 kelvins, and here we have 413 kelvins. In both the cases, we use concentrated H2SO4 as catalyst, and what we get in first case is CH2 double bond CH2 plus H2O. This is nothing but ethene, and in second case what we get is CH2 CH3 CH2 O CH2 CH3 plus H2O. This is ether, it's more specific, ethoxy ethane. Thus, by doing so, we are able to, there are two different ways. The first one here, the first case here is intramolecular, and the second case here is intermolecular. We can also go through the mechanism of the whole thing, let us understand how this works. So there are three basic steps here. The first step, I'm talking about the mechanism. There are three basic steps. The first step would be protonation of ethanol. You know, why would we try to protonate ethanol? I have already told you that by doing so, we can convert OH into a good leaving group, and at the same time also generate a strong positive charge on carbon. So now this carbon that we have here, this carbon here, it becomes our electrophilic center, something which is positive and would want to take electrons. So we generate electrophilic center on one of the carbons, right? Now in step number 2, this was step number 1. In step number 2, this one more molecule of ethanol now performs a nucleophilic attack on the partially positive carbon that we know, the electrophilic carbon, right? And then there is this, water leaves, and what you get is CH3, CH2, OH plus. Remember, once when oxygen uses its lone pair and donates it somewhere, then this oxygen attains a positive charge, as you can see here. And then we have this CH2 and CH3. Along with that, we put water. This is like your protonated ether. And in step number 3, your ether is now going to lose your CH3, CH2, O plus, H, CH2 and CH3. Now this is going to lose its proton and form an ether. Thus your acid is regenerated back, so it acts as a catalyst. So this is the full-on mechanism, This is the full-on mechanism of what we have. Yeah. Yeah. So I think this was the first part, right? Here we have to know a few things here, right? One thing, some important things to note down here. By this method, primary alcohols are ideally converted to ethers. The reaction occurs by the attack, nucleophilic attack is SN2 attack. Where do you have your SN2? Did you figure out where your SN2 attack is? Your SN2 attack is this nucleophilic oxygen of alcohol. It attacks the carbon here. So this is SN2. You may even put SN2 here directly. So I can directly put this is where your SN2 attack is. And so that's the second point which is to be noted down, that here the attack is SN2. And the third important thing is that you cannot really take secondary and tertiary alcohols prefer undergoing elimination and form alkenes rather than ethers. So it is very important to know that secondary and tertiary would not work here, right? This is also a very important thing. And there's something more that you have to know, that what would happen, or how would I be able to generate, as they've given in the textbook, how do you generate an ether like ethyl methyl ether? If ethyl methyl ether is our target molecule, then can you figure out what should be done? So in that case, obviously obviously you might think that we might take up ethanol, right? And you may take up, for the intermolecular reactions, we may take up methanol to get a methyl ether, and then we may use concentrated H2SO4. Here, what would you expect? Yeah, as per what you think, yes, this is one of the products. Right? This is one of the products. But is it not possible, just think, is it not possible that two molecules of methanol react with each other, or two molecules of ethanol react with each other, the way it happens here, right? Where two molecules of ethanol are made to react and we get diethyl ether. Here also we've taken ethanol, there is acidic conditions. So is it not possible that two molecules of ethanol may react with each other? Yes, it definitely would occur. So there are some byproducts, and in all there would be three products formed. So CH3, CH2, OCH2, CH3 is one, and you may even get two methanol molecules forming dimethyl ether. So if you take two different alcohols for the same reaction, then you may end up in getting three different products, and this is one of the biggest problems that we face, right? So I think we can have all this grouped together. Yeah. So I think you also understand the problem of producing a mixed ether. If you try to produce mixed ether by taking two different alcohols, then you may end up in getting three different products. This is one example that is discussed in our textbook, and they have not given the answer, but here I have shown you what might happen if you take two different alcohols, right? We now move on to the next method of preparation of ethers, and that's Williamson's ether synthesis. So now Williamson's ether synthesis. Now, one of the important things about Williamson's ether synthesis is that this is one of the best I'm sorry, this doesn't work. I don't know why. It isn't working. So just a moment, I'll be... so now things are all right. Let us start with this. Williamson's ether synthesis, as I've told you that this is one of the very important methods for ether synthesis. One of the things that is so important is that it is a laboratory method. So you can do it on an industrial scale, but it is an excellent laboratory method because the method is so simple that it can be carried out easily in a laboratory. Another important thing, simple and mixed ethers, both can be effectively synthesized. So this is also a very important thing. See, in the previous method we had a problem, right? We had a problem that we could not synthesize mixed ethers, right? I did show you that there was a problem with that, and if you want to have a look, I think this is where it is. Two different alcohols giving you three different products, right? So you get the target product, but along with that you also get some byproducts. Now in Williamson's ether synthesis, even if you want to make mixed ethers, I think you can very easily make it without forming any byproducts. Now what exactly is the reaction? Let us understand that. The reaction is ideally an SN2 attack. It is a nucleophilic substitution reaction. Primarily it is SN2, and the reaction begins by taking RO minus and Na plus. This is what we call as sodium alkoxide, which is our nucleophile in this case, and it is made to react with Rx or R-X, and this is our alkyl halide. The reaction goes like this. You have your oxygen which is acting here as a nucleophilic center. It can attack. So we have out and out SN2 forming RO R- plus NaX. So this is I may make a I may note this down here. Let this be called SN2. So this is SN2 attack, and I think that's one of the fundamental things here. So this is your reaction scheme in which an alkoxide is made to react with alkyl halide to give you your corresponding ether. Now certain precautions that you have to know here, because it's very, very important. Okay, suppose you want to make a target ether which is a mixed ether, and it is something like this: CH3 C CH3. On one side you have a tertiary alkyl group, and the other side you have a methyl group. Suppose this is our target ether. This is like tertiary butyl methyl ether, right? And IUPAC name could be like IUPAC would be 2-methoxy 2 methyl propane, because your parent skeleton here would be something like this here. This is your parent skeleton, and you have to number the parent skeleton in such a way that your substituents get minimum number. So this is your target ether. Now the question is, I have to take one alkoxide and one alkyl halide. Just remember one thing. So there are two parts here, right? I can divide this molecule into two parts, right? So it can be like, one part is this. There's one alkyl group, and then there is this another alkyl group, right? And they are bound through oxygen. Now remember, the bigger alkyl group, you always take the alkoxide. And the smaller alkyl group, you take the alkyl halide. So the source of smaller alkyl group will always be alkyl halide, and the source of bigger alkyl group, more branched alkyl group, should be an alkoxide. Now this would give you a perfect ether. I would show you why. So I need to take CH3, 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 and I need to take an alkoxide here. And for the smaller one, I take an alkyl halide. Now the reaction goes like this. Oxygen, and you have this plus NaCl. Now you can see that you always do this. If you don't do this, if you take the reverse, let's say first of all, this is called sodium tertiary butoxide, and this is methyl chloride, right? And this is how you get your ether. Now once again, let me group this up. Everything gets grouped up now. All right. So we can have, we can have this going here, and we can have this along with it. So basically, this is the reaction that we get, right? And now let us assume that we do the reverse. For example, if we try to do the reverse once again, right? If I try to get the reverse thing, right? So let us understand that. Suppose if I take CH3, O minus and Na plus CH3, C, CH3, CH3 and Cl. Now you know that tertiary alkyl halide, very easy for dehydrohalogenation. The elimination reaction, we call this. We have already done this, that in any substitution there is a big possibility of elimination, and when you have a tertiary alkyl halide as your substrate, then the possibility of elimination with a strong base, now here it acts as a base, with a strong base like methoxide is very, very high. So this goes here, this goes here, and you end up in a product which is like, first of all, here you get CH3OH plus, now you have CH3C double bond CH2 and CH3 plus NaCl. An alkene gets formed. So if you try to do the reverse, there is a big possibility that you end up in getting only an alkene. And that's one of the important things to know, that you have to see to it that you do it properly. If you don't do it, if you don't do it the right way, you end up in getting only an alkene. So Williamson's ether synthesis is a very good reaction. However, you have to see to it that when you have to make an ether, the bigger alkyl group, right, is always taken from the alkoxide, and smaller alkyl group is always taken from alkyl halide. This is something which you have to know. Otherwise, you end up in getting an alkene if you do the reverse, right? The same technique can be used for, phenols. Phenols are more acidic than alcohols. So all you need to do is, when you take any phenol and you react it with NaOH aqueous, this is a phenol, it would first of all give you a sodium phenoxide minus H2O, and here you get sodium phenoxide. And this sodium phenoxide can be further treated with an alkyl halide, anything like CH3Cl. And now in that case, you find that there is SN2 attack. I may even show chlorine a little away so that I can show that this leaves, and you end up in getting OCH3 plus NaCl. This is methoxybenzene, also known as common name anisole. Thus, this is also a good example of Williamson's ether synthesis, and you find that phenols would also undergo such Williamson's ether synthesis. Okay, so this is more or less from the book part that we have. Next comes physical properties. Okay, let us take up the physical properties now for ethers. Now, ethers have, the bond, CO bond, in ethers is polar, and hence ethers are weakly polar molecules. So how would this impact their respective boiling points? Let us understand that. If you want to compare the boiling points of ethers, you may say ethers have higher boiling points than alkanes. with comparable mass, right? Generally, if you compare the number of carbons in an ether with 4 carbons, and if you take an alkane with 4 carbons, I think ethers would have slightly higher boiling points. That's all. However, boiling points of ethers are much lower than alcohols of comparable mass. That's because of what? What do you think? That's because of? This is due to inability of ethers to make intermolecular H bonds like alcohols. So if a question is asked, why do ethers have lower boiling point as compared to alcohols? Your obvious answer would be like, ethers have no capacity of making intermolecular H bonds, while alcohols have a tendency to make intermolecular H bonds. And that is the reason why alcohols have higher boiling points and ethers have lower boiling points. This is something which you always put in your answer. And another point that we have to discuss here would be the tendency of ethers to get soluble in water. So here we write aqueous solubility of ethers is comparable to alcohols, as both have capacities of forming H bonds with water. I can show you the H bonds of ethers with water. For example, if this is ROR, right, then you have this water molecules you can have some H bonding taking place here, and this H bonding is responsible for solubility of ethanol in water, solubility of ethers in water, and this solubility is more or less comparable to that of alcohols, because like alcohols, even ethers are able to make hydrogen bonds. All right, let us start with chemical properties. The first chemical property is about breaking the CO bond in ethers. Now, let us first of all understand the reactivity of ether. Ethers are low in reactivity, and so CO bond breaks under drastic conditions. Only. Now, how is this bond broken? The bond breaks in presence of halogen acids, right? HX. The order of reactivity of halogen acids would depend on the acidity. The strongest acid reacts the most and the fastest. The rates are maximum. And then we have, so these three halogen acids in principle can be used, and you know that the order of reactivity is excellent with HI because it is the most acidic of all three. Generally, reactions are accomplished using, the reactions are accomplished using HI and HBr. So generally we take concentrated solutions under drastic conditions. So we have to, HCl generally is not preferred because the rates are too low. So these two are generally used, and more preferred is HI for breaking the CO bond in ethers. So let us now take the mechanism and understand how exactly this happens. So first of all, let me make this group this up. All right, so let us go to the next part. Okay, I'm trying to go through the mechanism. Let's say we have ether and there is this, HX used. Now, the first thing that happens is, let us take up an actual ether to understand this instead of taking this general form. So I am going to take up something like this: CH3, CH2, O, and then CH3. Right? What do we call this? This is ethyl. Common name is ethyl methyl ether. And let us allow this to react with a halogen acid like H plus and I minus. The first step is protonation, in which the lone pair would capture one of the H plus here, and this would give us a protonated ether. This protonated ether has positive charge on oxygen, and we have to name this also. We call this as protonated ether. Now this protonated ether is then subjected to a nucleophilic attack by iodine. So iodine here would act as a nucleophile, and it would attack the alkyl group, which is smaller. So here I say this is SN2. Because it is SN2, it always goes on to the alkyl group, which is smaller, and this goes here. So we say here, note I minus attacks the smaller alkyl group, right? And this would result into what? This would result into CH3CH2OH plus CH3I. This is step number 1 that happens. Right? Now, step number 2. If HI is taken in excess, then the alcohol formed reacts with it to form corresponding alkyl iodide as the product. Let us understand that. How would this go? This would be like you have CH3, CH2, OH with HI. Like ethers, alcohols are also protonated. So this first step is protonation, which always converts any alcohol into a good leaving group. The OH of alcohol gets converted into good leaving group, and there is a reasonable amount of electrophilicity which is attained by this. So this would become partially positive, and now this is subjected to SN2 type of nucleophilic attack, and in this attack you have your water lost and CH2I plus H2O. So if you use alkyl or if you use your halogen acid in excess, then both the alkyl terminals here, they both get converted into corresponding alkyl halides, and this oxygen gets converted into water. So overall, in presence of excess of alkyl halides, you find that this becomes CH3, CH2I. This also becomes CH3I, and this gets converted into water. So this is something which you have right? So you need to understand how exactly the reaction goes. So I am now going to give you the summary, right? First thing, if you use HI, let's say if you use only 1 mole of HI, then the smaller alkyl group becomes alkyl iodide, and the bigger alkyl group becomes an alcohol. If you use excess, then the bigger alkyl group also gets converted into a corresponding alkyl iodide. The same would happen if you take HBr or even HCl for that matter. If they give you a reaction, you have to put chlorine or bromine here instead of iodine, right? But the reaction would proceed exactly in the same manner. Okay, so let me now let us group this. Let us hope everything goes well. Just a moment. A few things left. Just a moment. This was left here. This was left here. Now I think should be okay. Oh, you still have problems? No problem. Just put it over. All right. I think this is what we have. This is the first part, right? Now the question is, because we took an ether here, which was like a simple, normal primary alkyl groups. Now what would happen if you take a more, branched ether? So let us take up this example, CH3, C, CH3, CH3, O, and CH3, and we allow this to react with 1 mole of HI. I'm putting 1 mole, not excess, 1 mole. Now in that case, what would happen? The first step, the first step would be the same, wherein you will have the protonation taking place. However, here the alkyl group present is a tertiary alkyl group, and you know that tertiary alkyl group forms a very stable carbocation. So now in the next step, what happens is your tertiary alkyl group actually gets separated. So before I minus attacks here, you have your carbocation generated. Plus, and then you have CH3OH. And now this reacts with I minus, and this I minus then gives you a corresponding alkyl halide. It is very important because this carbocation as an intermediate which is formed here, it is very important that this reaction should take place in aqueous medium. So it is very important for us to write aqueous. It is very important for us to write aqueous here because this is, very important for us. Yeah. So we group this up so that we have this. All right. So now what do you understand from this example that we have taken? Generally, the bigger group becomes an alcohol and the smaller group becomes a halide. However, if the bigger group is a tertiary alkyl group, then the tertiary alkyl group becomes a halide and smaller group becomes an alcohol. Exactly the reverse of what you normally observe. Pay attention here. Many questions are asked from this part. Please note this down. Under normal circumstances, if they use only 1 mole of HI, then the smaller part becomes alkyl halide and the bigger part becomes alcohol. If they use excess, then both of them would become corresponding alkyl halides and oxygen would become water. On the other hand, if they use only 1 mole, then smaller part becomes alkyl halide and bigger part becomes alcohol. However, if one of the alkyl groups here is a tertiary alkyl group, and if you use aqueous HI 1 mole, then you have to decide which part becomes alcohol and which part becomes alkyl halide. In that case, the tertiary alkyl group becomes a halide and smaller part becomes an alcohol. Just the reverse of what we observe in first case. Pay attention. This is going to be very important for exam, and you have to do this properly. One more thing. Now let us break the bond, a similar bond, CO bond, in in phenyl ethers, right? So one more reaction that we need to understand, which is very important, and that is, if you take a phenyl ether where one of the alkyl groups is a phenyl ring, and then when you use HI here, excess or 1 mole doesn't matter. Excess or 1 mole doesn't matter. It is always aqueous, and let's see what happens. First step is protonation, as always, and this protonation would give you now there is a possibility of 2 bonds to break. Here either this bond can break, in that case we get methanol and iodobenzene. Iodine goes here, and if this bond breaks, then we get phenol and we get iodine with CH3 to form methyl iodide. Now remember, here you have to remember the rules here. Consider these 2 bonds here and let us understand what they are. This is formed by sp2 carbon of ring, so small and difficult to break. Whereas this bond here is formed by sp3 carbon of alkyl group, and hence it breaks readily. See, a more electronegative carbon here would make this bond stronger. A less electronegative carbon here would make this bond slightly, weak and so easy to break. So let us start here. We say, now in the next step, your iodine is going to attack the substrate where it finds the maximum, potential of breaking the bond. So it goes like this, and this bond breaks. So what happens then? You get phenol and you get methyl iodide. And therefore this is your phenol and this is methyl iodide. So basically what happens here is, you find that every time when you have a benzene ring, every time you have something like this here, a ring and OH, remember the bond between the ring and oxygen never breaks, irrespective of what you have here, whether you have a primary alkyl group, secondary alkyl group, tertiary alkyl group, anything. Don't worry about it. Never ever break this bond, always break this bond. So the negative ion always attacks this alkyl part, irrespective of whether it is primary, secondary, tertiary, whatever. And this bond breaks always, and the 2 electrons go on to this oxygen every time phenol is one of the products which is obtained. Even if you use excess of HI, now HI cannot convert OH into I because this is on the ring. So even if you use excess of HI, the products remain the same because OH cannot be converted into I it cannot be replaced by iodine because this OH is on the ring, and such substitutions are not very easy with OH connected to the ring. Okay? Now the second property that we talk about is electrophilic substitution. Now electrophilic substitution is possible in aromatic ethers. Now aromatic ethers, all right. So aromatic ethers, right? What are they? Generally, these are also called the phenyl ethers. So when you have a phenyl ether, it'll have lone pairs on oxygen, and these lone pairs of oxygen, they are in resonance, they are in conjugation with the pi bond, so they generally, show resonance, and this would result into negative charge of the ring increases, and then there is this lone pair becoming a pi bond becoming a lone pair, and this continues. I can put my and then we have this. So basically, if you properly understand this, there are two things you can infer from this. One, you find that the negative charge gets more accumulated on ortho and para positions. So these are the most reactive sites. So we say here the alkoxy group is ortho and para directing. The alkoxy group is ortho and para directing. That is one thing you have to know. And the second thing that you have to know is ring gets activated as electrons move into the ring, making ESR, electrophilic substitution reactions, ESR, making electrophilic substitution reactions easy to occur. So this is like, what we have with right? So basically, there are two things that when you have an alkoxy group on the ring, electrophilic substitution reactions are more easy to occur, and that's because of activation. And two, the alkoxy group is ortho-para directing. So let us take up some of the unit processes or the basic reactions, right, in this category. The first one that they have given in the textbook is bromination. Now, the reaction seems to be okay and easy. How would we do this? A simple, we take any sol, OCH3 as our reference molecule, and we allow it to react with bromine in presence of CH3COOH. Look at this. We do not need FeBr3. Generally, we use FeBr3. Generally, we use FeBr3 for you know for our reaction. That is to form Br plus the electrophile. But here, active FeBr3 is not needed because the ring itself is extremely activated, and so what we have is we have two products, ortho and para. So it is like 2-methoxy and or para-bromo anisole and ortho-bromo anisole. Now remember, due to steric hindrance, this is always major and this is always minor. So 2-bromo anisole, this one here is 2-bromo anisole and this one here is 4-bromo anisole. So this is the first reaction. The second reaction that we take up here is Friedel-Crafts reaction. Friedel-Crafts reaction. In this we have two, Friedel-Crafts alkylation and Friedel-Crafts acylation. So we have two of them now. So let us first of all highlighten this. Let us move to the next category, Friedel-Crafts reaction. Friedel-Crafts reaction can be done on phenol, on anisole, the ether. And the conditions are still the same, the standard conditions. You can use CH3Cl and anhydrous AlCl3. If you have to use a solvent, you can use a non-polar solvent. In textbook, they have written CS2, carbon disulfide, a non-polar solvent. Or you can avoid writing that solvent also. It is okay. And the product here would be OCH3 with CH3 in ortho. And you can also have OCH3 with CH3 in para. So we may have methoxytoluene. This is like 2-methoxytoluene. And this is 4-methoxytoluene. And remember, again here, the major product is a para product for a simple reason that there is less steric hindrance. A similar reaction can be given for, I can have my ruler pressed here. And now I can have my arrow here. This is like CH3COCl acid chloride, and you can have anhydrous AlCl3. And this can give me again two products, OCH3 and then we have this COCH3 in ortho. This is always 2-methoxy acetophenone, and this is minor plus. This is 4-methoxy acetophenone, and this is going to be your major product. So now you have the Friedel-Crafts reaction here, one producing toluene, methoxytoluene, the other producing methoxy acetophenones. Okay, the same reactions, right? No big difference in all these reactions. And then we have the last reaction, which is the third reaction, which is nitration. Nitration has I can put up nitration here. And nitration here is about anisole reacting with nitrating mixture. Nitrating mixture here could be concentrated HNO3 and concentrated H2SO4. This would result into two-nitroanisole, as they call it, and this is 4-nitro. Anisole, and obviously this is going to be your major and this is going to be your minor, again based on steric hindrance. So we've completed all the electrophilic reactions which are given in the book. Now my request would be, go through all the in-text questions and all the questions which are given at the back of the chapter, and you may ask your difficulties in my regular lectures and I would be solving them.